Okay, so let's continue. So this is the last part of this two-dimensional random tomography problem. And so this is the main reference. As we want to, as we mentioned, this is a two-dimensional tomography, and we want to, in this last part, we want to study how to handle noisy projections. Okay, as we discussed in the first part of the lecture, you remember the projection direction is unknown, and each data point as a projection image looks like this guy, which is the clean data plus noise. And we want to recover the projection angles so that we can apply inverse X-ray transform to get the image recovered. And this is doable. This is doable because the X-ray transform actually has some integration parts. So the central limit theory, the law of large number comes into play so that you can still get something reasonable. But as we also discussed in the first part, diffusion map actually doesn't work. It gives you some crazy angle recovery so that you cannot get anything reasonable back. And our goal, as we also discussed in the end of the first lecture, is trying to denoise. Trying to denoise the noisy projected images so that we can get clean, cleared, denoised projection images so that we can recover the projection angle and apply diffusion map and so on. So that is our goal. Okay, so to achieve the denoise, we will apply some basic ideas from spike model or matrix denoise, and which we discussed in the second lecture. And so this is the basic idea, similarity. So if you remember, we have S1, you have X-ray transform, you get projected images and so on. Now, if you pay attention, there is an interesting fact, isn't it? Although they are different in detail, but overall they look similar to some extent. Not exactly the same, but similar. So, what we can consider is, hey, this is the Radon transform. Sorry, this is a sinogram of the X-ray transform or Radon transform because it's two-dimensional, so they are the same. This is the sinogram image, the matrix. Somehow, you see, every part, they have some kind of similarity. It's not totally different, but also not the same. We consider the following spike model to describe this fact. So we would model the noisy data by a matrix Y, which is X plus C. What is X? X is kind of the sinogram, and remember, we will randomly sample points on theta S1. So this is the X part, the random sample part, and the C is the noise. Okay, so we will say that, hey, look, X, which comes from randomly sampled on the X-axis from S1, and put all the sample point on S1 as a matrix X. This is a random matrix with no rank covariance. Why? Because as I said, they look somehow similar, right? Similar, so they can be well described by few structures. That is a basic idea. And you can see it's just a random matrix with IID entries. IID entries. And this is the summation of the assumption. We say, hey, the expectation of X, this matrix, is actually mu, which is the common component or structure. And you have some kind of low rank covariances that describes how the structure changes from one angle to another. And the noise is 0, and the covariance is sigma squared IP, IID entries. It doesn't need to be really, it doesn't really need to be Gaussian, but it just needs to be IID. We can consider more general noises and so on, but we will be satisfied in this lecture about IID noises. And for the more general noises, structures, we'll discuss them in the future. Okay, so this is what we have mentioned in the second lecture, but just have a quick recall. Under the spike model, okay, in particular, you can see it's white, and you can see an X have finite force moments, and assume lambda is simple, and so on. And if lambda is not simple, then we just change everything to eigenprojections and so on. Then the eigenvalue and eigenvectors converges with probability 1 to the ground truth and so on. So you see, the point here is all the eigenvalues and eigenvectors of the simple covariance matrix will be biased. And if the low rank signal part strength is too small, then you even cannot get anything back. Okay, so that is what we discussed in the second part of the lecture. So, what can we do under this limitation? So we cannot, well, seems that we cannot do too much. But turns out, well, we can still do quite a lot. For example, you can see, hey, this will be the eigenvalue distribution. When the signal to noise ratio is 20 dB, you see, there are some very big ones. Good. Noise is increasing, even 0 dB, you see there is something increasing here. Okay, and this part seems to be increasing quite big, quite good. Increasing, right? Increasing, even minus 10 dB. You see, you can still get some eigenvalues that seem to be relatively big. So overall, although we have some bad news from theory saying that eigenvalues and eigenvectors are biased, but they seem to still follow some good structures. The big eigenvalues still seem to perform relatively well. And if you take a look at eigenvectors, you see the top one, this row, and this row, they are clean eigenvectors without noise. And you can find eigenvectors of the simple covariance matrix from the clean data. And you see, hey, they're very nice, right? There are some good structures. And look at the noise. This is when signal to noise ratio is minus 5 dB. You can see that, hey, this one, the top singular vector, looks very similar, right? Although we know it is biased. It is biased because there are some kind of crazy, well, and when eigenvalue decreases, even up to the fourth eigenvector, you see they look still quite similar, isn't it? And you can increase, even up to 6. You can still see some structure from the noisy representation, isn't it? You can still see something. And starting from 7, well, it's really hard for me to say anything. Even if I stare at the ground truth, it's difficult for me to say anything, right? And you lose everything, you lose all the information. Okay, but up to 6, it seems that you still can say something. 5, you can still say something. And if we come back, this is minus 5 dB, right? 1, 2, 3, 4, right? Roughly 4 top eigenvectors seems to be okay. 6, 5, it's hard, really hard to say. And that is reflected somehow, okay? But certainly, it's very nonlinear, so we cannot really say, directly say too much. That is observation. Look, this is observation from simulated data. So, we now understand there is bias. But with the bias, we still have some good structures. So what can we do? So what is the best way to denoise? Okay, people may say, hey, you want to denoise, right? And it's an image. So maybe we can use L1 minimization, sparsity, and so on. Wavelet is a good tool. That is true. But turns out, we will see in a bit, that doesn't really work that well, in particular when noise is very big. We need something more adaptive to the data. Because wavelet, somehow you have to pre-assign some information, but that information, in particular wavelet itself, may not fit the data structure. So we want the data structure to speak out of itself. That will be the overall goal. And so we will think about the Wiener filter perspective. We will consider this kind of structure, this kind of minimization problem, from clean data and noisy data and so on. That will be the overall idea. But how and why we want to consider it, and that is a kind of something you can see details in the paper. Let's see why we want to get it and how we get it. Okay, how? Okay, again, that is the overall structure, the same model. I just repeated here. Okay, so a possible optimal estimator of the projection image is what? You try to evaluate conditional expectation and maximize it, because this is the observation data you have, and if you are able to get x hat, then everything's good, right? But you know, hey, this is kind of dreaming, right? Because we don't have this kind of conditional expectation information. We cannot do it. Not practical at all. So we need to do something. To handle this term. And the very basic idea we can imagine is, let's try to remove the conditioning on y. Second, it is still, even if we remove the conditioning on y, it's still very nonlinear. So how about if we consider a linear approximation? We just consider linear approximation. That is a very simple structure already. So let's see, suppose this is what we want. Then, if we can optimize this guy, can we achieve a good optimization or a good denoise? And if you look at this guy, this is nothing but the right-hand side. You can solve it directly. And this is a very simple, very commonly used Wiener denoising approach. However, this Wiener filter, if you think about it, it is maybe not super suitable for us. Why? Because look, we do not have sigma. We don't know sigma. The covariance structure is unknown to us, and we already said we cannot recover it. The recovery is biased. So what can we do? Let's take a look. This is a solution, right? And now we can rewrite it in this way. We can rewrite this in this way. That is, you have sigma, and you just write its eigenvalue decomposition in this way, and you define signal to noise ratio as the eigenvalue divided by sigma squared. This is noise strength. Okay, so that this formula can be written in this way. Okay, which is nothing but y minus mu project to case eigenvector, and you do some weighting. And this weighting depends on the signal to noise ratio. Okay, so this is the starting point of what we will do. And now SNRK can be considered as the signal to noise ratio of the case component. And now, from here, we want to ask the question about how to handle the unknown covariance matrix, unknown eigenvector, and unknown eigenvalue. And as I said, right, it's not a problem when n goes to infinite and p is fixed, but it is a problem when p and n are both big. That is, p depends on n, and p over n goes to a finite constant. It's a large p, large n model. We do have some problems, right? And how to understand Wiener filter under the large p, large n setup. That is our goal. And the basic idea is very simple. Let's modify the Wiener filter. Just do some modification, and then try to take the bias into account and do some modifications. For example, let's introduce HK, which is the filter coefficient coming from this optimization. And we want to find all these coefficients, HK. And what you do is just a sequence of rewritten of this function. And I will not. And this is just something you can do it at home, and you get this guy, and then this guy, and then since C is binoise with variance sigma squared independent of x, blah blah blah, so you will get all this simplification, further simplification. Okay, so you get this guy, and you get a solution. You know HK is this guy. You have sigma here, capital sigma here, covariance matrix, sigma squared, the noise level, and all the other quantities. Is this the answer? Not really, right? Because you see, look, sigma is still here. You still do not solve the problem, right? There is still mu. Mu you need to estimate it. Sigma you need to estimate. There are still several things you need to estimate. So there are some facts that help us to achieve that estimation. First one, you know the sample mean will converge to a true mean, so everything is good. The second one is in the spike model, you can show that the sample mean, sample eigenvector and the population eigenvector, if k and l are different, actually they will converge to zero almost sure. Okay, and then you can see the proof in the paper. I will not do it here. You just use the spherical properties. And so that the unknown sigma can be written down in this way, which converges to lambda k c k squared. So this term is simplified. And hence, hk is reduced to this way. And it can be written as the formula SNR gamma k. And this gamma is what? Gamma is the limit of p over n, right? And you can define SNR gamma k as this guy, which is written in this way. And this is when SNR k is greater than or equal to square root of gamma, or 0 if it is less than square root of gamma. And if you look at this guy, this is actually a new SNR that is modified by gamma. That is why we put gamma here. And this is actually a better definition of signal to noise ratio under the large P and large N standard. So finally, we achieve the desired denoise algorithm. This guy. And the only thing that remains is how to get mu. And the mu is actually can be estimated using sample mean. And what we need further will be, well, how many eigenvectors, eigenvalues, or the rank is needed. And that can be estimated, well, using some existing tools. But we will not discuss details because those are kind of for IID noise, and we will discuss this rank estimation in the future lecture under more general noise and so on. But you can see there are some literatures in this direction. Very good. So we have an algorithm. Now let's see what we get. This is the result, and this is what am I? Okay. So we have this is a 2 dB result, and this is yes, using a Wiener filter denoise. The blue one is the noisy data. The blue one here is the ground truth. The red one is the denoised one. Okay, on the right hand side, this is using wavelength. The red one is using wavelength. Okay, so you can see quite a lot of detail is ignored in wavelength. Denoising, which is called spin cycling technique. And these are 4 different projection angles, and you can see using PCA or using this matrix denoising, you let the signal to tell itself to determine what is the best basis, and the basis is actually determined by eigenvectors, and then you get some kind of a better result compared with spin cycling. And when noise is even larger, remember I have a larger one? Yes, this is, well, I don't remember. Oh, this is minus 5 dB, yes, minus 5 dB, larger noise. Then you see somehow wavelength will give you something, well, not really informative, but PCA still gives you something meaningful. Very good. Now, before we put everything together, there are some small geometric structures and the tools that we can leverage so that we can better denoise the signal, denoise the algorithm, get a better result. So let's take a look at an interesting geometric structure. So the first one is we need to ask, what is the limit of this PCA approach to recover the phantom? That is, how many principal components do we really need so that we can see the manifold structure, the one-dimensional manifold structure, CP. If you just do a linear embedding of CP by the top two principal components, then that is what you get. You see, there's a very obvious an intersection. It becomes an emergent. So the manifold structure is destroyed. The topology is destroyed. You cannot get anything back. And now, maybe that is because of, well, PCA, which is not good because PCA is linear. So you may say, oh, this is because of linear, but so blah blah blah. Okay, good. So how about if we try diffusion map, which is not linear? Maybe we can recover phantom. So what you do here is you just run diffusion maps of the linear embedding of CP by the top K principal components by PCA. Then you see if you use the two principal components and combine with diffusion map, that is a diffusion map of this guy. Sorry, you still get the intersection. How about 3 intersection? But starting from 4, if you use 4 principal components, well, good, you get S1 back, K5 S1 back, which says that you need to have at least 4 principal components so that the projection images provide sufficient information to get CP back, to get the angle ordering back, so that we can run the desired inverse X-ray transform. And why? Okay, so just a quick recall about principal components. And if you do an observation, you will see, hey, look, this is like even, right? Centered at 0 is an even function. Centered at 0 is like an odd function. This is like an even function. This is like an odd function, right? And this is an even function. This is an odd function centered at 0. So there are some structures that we can leverage. So what you can do is, you see first the mean, mu, and the u1 are even, and the u2 is odd. So what you can get is the Laplacian transform or X-ray transform of S can be written as mu plus the first eigenvector, second eigenvector, and so on. And you have coefficients that depends on theta. Very good, easy. So now you try to find theta star such that A2 theta star is 0, such that R theta star F minus mu is perpendicular to U2. How can you do it? That is a very simple calculation you can achieve, and by contiguity. Okay, so that is what you get. So you say, hey, you can find theta star, some specific projection direction, such that A2, the second coefficient, is 0. So with reflection, you can get self-intersection since the following calculation. Now, at theta star, A2 is 0. So this guy is done. So you have these two remain. So you can take minus theta star, this is minus S, and you can put everything into. And because mu is even, okay, U1 is even, so you get the same thing back. So you see, the over theta star, if you flip it back, okay, you can get something exactly the same. And so from here, it tells you that you should have at least 1, 2, 3, and 4 eigenvector, so that you can get what you need. So you need at least 3 eigenvectors to avoid self-intersection. Okay, and there's a small trick that can help. The small trick is the following. You see, hey, if you do a projection, sorry, if you do a flippation, which is theta, and you have theta plus pi, and this theta plus pi, this is minus S. So maybe you can say we can directly double the data by reflection. Maybe you can say so. But this might not be a good idea, because if you just directly double it, the noise will be dependent. And you don't want dependent noise. You want noise to be independent, which is better. If the purpose is using central limit theory and so on. And again, just take a look again. You see, it is either even or odd. Even or odd with related to 0. And this is a noisy data. So a very basic idea is, how about if we think about just the health of the data, just health of the data, so that we can get the even part and odd part. So that in the end, the sample covariance matrix is of size p by 2, not just p. So in this case, you somehow reduce the gamma by half. And if you reduce gamma by half, then you can eliminate the high dimensional impact by half. And that can better improve the overall accuracy. Okay, so reduce the dimension by 2. And the final trick is Jaccard index. And this is a very basic idea in from social science or so on. The basic idea is saying that, to see if two guys are really friends, then you can just examine their friends. If they have many common friends, then with high probability they are real friends. They're really friends. So what you do is you can denote Ni to be the set of vertices connecting to vertex I. And you define J, Ij, to be this quantity. How many intersection divided by how many union? If two friends, two guys, they are really friends, their common friends should overlap quite a lot. But if two guys, they are not really friends, then their friend groups may not overlap that much. So that is the basic idea. Okay? So all these quantities can be quickly implemented numerically. So you can use matrix to implement it, and so that Jaccard index can be used just run this matrix calculation. So easy, quick. And with that Jaccard index, you can set a threshold, say beta is 0.5, so that when you use, the affinity distance, L2 distance to determine if 2 points are really neighbor, you want to connect them. When you after you connect them, you can use Jaccard index to decide if they are really neighbors. If they are not, Jaccard index is too low, then you just remove that age, even if their distance is small. So when signal to noise ratio is -4 dB, and you do not run Jaccard index, you just use L2 distance to determine who is the neighbor. This is the result you get. Okay, so what am I writing here? The picture here is you have all the sampling points on S1 because we know the ground truth, so we just observe how points are connected. When signal to noise ratio is -4 dB, then you see there are a lot of strange lines that connect very, very far away points. But if once you apply Jaccard index with threshold 0.5, then you see a lot of false connected points, false edges are removed, and that can improve the quality of diffusion map when you apply it to recover the ordering of the projection angles. Finally, we can put all together and see how good we get. What is the final result? This is a 2 dB result, and this is actually the limit of what people can do before that paper. And then we can go beyond it. Minus is 1 dB, 0 dB, -1 dB. You see, there are some kind of interesting thing right here. There's always some kind of small errors. That is because there are some patterns that are very similar, so it's very easy to get confused in these regions. But you can still get something reasonable back even in -1 dB. You can further go -3. Okay, -4 is almost difficult. You cannot see too much. -5 totally fair. Okay, you can, well, consider more. For example, we also considered trying to, well, include L1 minimization and so on. But L1 minimization in the reconstructed images and so on, well, you can play with it, and you can see more results in the paper, but I will not discuss them here. So there are some more, some more tricks from image processing that you can apply. There's another approach, but we will not discuss it here. For example, you can view X, the projection images, as a deterministic restoring structure. And then that will be another set of denoising technique you can utilize, and that is what we will discuss in the future lecture. So FYI, in the later lecture, we will handle more general noise with different forms under more general setups, and usually it's called optimal shrinkage. Okay, and so you can view optimal shrinkage as the generalization of this modified Wiener field, and we will talk about it later. How to estimate rank or noise level, we'll also talk about it in the future under the general noise setup. And you can even leverage sparsity structure if there is one to reduce the dimension. Okay, and that is something, some papers we will discuss in the future. This is optimal shrinkage paper. This is more general noise paper, and this is when you have low structure noise. You have a sparsity structure. You can use, for example, wavelet to reduce the dimension first, so that P becomes finite, and you let N goes to infinite, and you use the traditional blah blah blah. Okay, so there are several ideas you can play with, and each of them, well, you need to do some fine tuning so that it can be successfully applied to different problems. Okay, so I think that is